My name is Jordan Kilburn, and I'm in charge of the power subsystem. Since this is a mobile project, power plays an important role in the overall success of the system. Two circuits were designed for this, one for the lead car and one for the following car. Both circuits are near identical, so I'll focus in on one. First, I want to start off with the power source, the battery. I decided to use a 5-cell 18.5 volt 3.6 amp hour lithium polymer battery for the following car. The reason a LiPo battery was chosen is because they have one of the highest power densities and extremely high power output. This results in a lightweight, small, yet extremely powerful source for the system. The biggest drawback of using a LiPo battery is their potential danger from overcharging and overdischarging. Each individual cell cannot be discharged below 3 volts or charged over 4.2 volts. However, this problem is easily fixed with a safety shutoff circuit attached to the negative lead of the battery. The shutoff circuit works in the following way. A simple and cheap LiPo cell measurement board is attached to the 6-wire test lead from the battery. This board measures each cell individually, and if a single cell drops below a predetermined set value, I use 3.3 volts to be safe, then a relay is tripped, resulting in the entire circuit being shut down. A reset switch is placed in the circuit to reset the relay after the battery has been charged. On the positive lead of the battery, we have the H bridges for motor control and a buck converter. The buck converter takes any voltage between 7 and 30 volts and steps it down to a solid 5 volts, or 12 volts in the case of the following car. The converter uses several input capacitors to reduce the load on each capacitor. They're used to smooth the input and allow fast current switching. The heart of this converter is the LM2678. This IC is perfect for the task because of its high efficiency and feedback comparator to adjust the voltage to the appropriate value. The LM2678 is basically a MOSFET controlled by a pulse width modulation. The duty cycle of the PWM is determined by the relationship output voltage equals input voltage times the duty ratio. Since we have a fixed desired output voltage, the LM2678 compares the input voltage to the output and sets the duty ratio accordingly. Increasing the input voltage results in a lower duty ratio and vice versa. I ran several tests to check the performance of the converter. The circuit performed better than I had hoped, and I was able to achieve efficiencies up to 90%. Here I have the circuit powering a Raspberry Pi. This was about 79% efficient when the Pi was idle. Running a few programs on the Pi to get the processor running at 100%, the efficiency went up to 87. This is the range that I designed the converter to be run at. Here the load is two 1.1 ohm 10 watt power resistors. I set the input voltage for 10 volts and the circuit pulled about 1 amp from the supply. This resulted in 5 volt output at 1.83 amps. Input power is 10.8 watts, output power is 9.15 watts, resulting in over 85% efficient DC-DC voltage conversion. At the ideal 9 volt input range, the buck converter showed a 90% efficient conversion. Future plans for the power subsystem include mounting the entire circuit to a PCB to increase efficiency and professionalism.
Hello, my name is Nicolette Schreier and I'm in charge of the image processing subsystem. The goal of my subsystem is to track the green ball attached to the leader car. It is very easy to filter images based on color. This was achieved through the Intel NUC. The NUC has a CISC architecture, which makes it capable of handling complicated instructions. Attached to the NUC is an HD webcam. The Python program grabs frames from the video stream. The first thing the program does is blurs the image and converts it to the HSV color space. Then the image is filtered for only the green HSV range values. The contours are defined based on the filtered image. The minimum enclosing circle of the ball is found from the contours. Then the moments of the ball are calculated to find the center point. This data will be used in controlling the follower car's speed and turning. And here is a video demoing the program running on the NUC.
Howdy, my name is John Henderson, and I will be talking to you about the controller subsystem. The purpose of this subsystem is to control the following car's steering and velocity via data fed from the image processing subsystem. The DC motors of the following car will be controlled via a PWM signal. I have decided that a PID controller will be the best approach for implementing this subsystem. A PID controller is a linear feedback controller with three terms: proportional, integral, and derivative. Each term is proportional to the error term. The error term is the difference between the set point and the measured value. Simply put, the PID controller's output is proportional to three different things: the size of the error, the duration of the error, and how fast the error is changing. The goal of the controller is to minimize error over time. Because the PID controllers only rely on the measured value of the process variable and not on knowledge of the underlying process, the three parameters must be tuned to fit for the specific application for which it is being designed for. A well-tuned controller will achieve system stability, reduce response time and overshoot, and minimize steady-state error. Some software which can help tune PID controllers is MATLAB Simulink, which I have been using, and National Instruments LabVIEW. Here is a screenshot from MATLAB Simulink's PID tuning application. The application supports automated and manual tuning. The following video demonstrates the PID controller which I have implemented to control the throttle of the DC motors using PWM from a Raspberry Pi 2. The top shows the PWM output on an oscilloscope, while the bottom shows the output of the image processing. The set point in this experiment is 20 centimeters. Notice how when the distance goes above 20 centimeters, the PWM increases up to 100%, and if the distance goes below 20 centimeters, the PWM will reduce until it goes to 0. This represents the car accelerating or deaccelerating. Future goals for the PID controller subsystem are to fine-tune the controller to get better response time and reduce overshoot, and to add steering to the control.
All right, so I realize that my subsystem is labeled here as wireless communication, but it should be more accurately labeled as sensors, because what I'm going to be doing is utilizing a microcontroller hooked up to an accelerometer on the lead car that will keep track of the changes in acceleration and wirelessly communicate that back to a microcontroller on the following car. And that will help control distance. And I'll also use a magnetometer to establish coordinate system and establish a heading vector that will also be transmitted back to the following car. This is a schematic for the accelerometer that is going to be used. It is the ADXL335 made by Analog Devices. It has a plus minus 3G sensitivity, the G being the same value of the Earth, or the acceleration due to the Earth's gravity. Is powered by a source of 3 volts, 350 microamps. The bandwidth is variable. You can adjust that by adjusting the capacitance at each axis output. The range for the X and Y output, or that can be seen on the right side of the screen. The range for the X and Y output are both from 0.5 hertz to 1600 hertz, and the Z-axis bandwidth is limited to 550 hertz. And normally for the Z-axis, gravity would need to be normalized, but our system does not accelerate vertically, so the output will remain unused at the Z-axis. When placed on the car, the X-axis will be forward-backward acceleration, and the Y-axis will be left and right acceleration. We may possibly normalize to one acceleration vector upon integration of our subsystems. This is the microcontroller of choice, the BeagleBone Black Revision C. It has a Citara ARM Cortex A8 processor with a voltage supply rating of 5 volts, 460 milliamps. It has 512 megabyte memory with an 8-bit 4 gigabyte eMMC onboard storage. Luckily, in addition to reading the sensor data, the BeagleBone can also supply the 3 volts required to power the accelerometer, as you can see by the multimeter reading of the voltage output from the BeagleBone, it is 3.377 volts. Since the subsystems have yet to be completely integrated, here is the schematic of the circuit I set up in order to ensure that the accelerometer is giving the appropriate outputs. Now, normally, the maximum output of the accelerometer is 3 volts, but the input tolerance for the BeagleBone's analog input pins are only 1.8 volts. So here, as the diagram shows, voltage dividers were used at each axis's output. I would show the actual calculations I did for the voltage divider, but it's, as you know, very trivial. So in the end, I calculated that the resistance values should be around 500 ohms and 409 ohms. The reason they're rather low is because the output impedance of the accelerometer's axes is naturally 32 kilo ohms, so that's rather high. So I wanted to keep it as low as possible so that I wouldn't have to adjust the impedance. So even though the output of the accelerometer has been adjusted to be able to go into the BeagleBone, like I said, we cannot use the output directly because it is a voltage. So we need to convert it to a value in G's, as in gravity. So the formula implemented within the code to calculate this is as shown on the screen. The acceleration in G's is equal to the value of the axis, that is red, minus the 0 offset, which is just a little calibration number, divided by a conversion factor. The conversion factor being because the value of the voltage output by the accelerometer is incrementally changed in accordance with the gravity, right? So with the resistances that I was able to calculate, that leaves a max output voltage from the accelerometer of 1.7 volts. So that means it goes from negative 3 Gs to 3 Gs between 0 and 1.7 volts, right? So at 0 Gs, the voltage would be half of 1.7, 0.85 volts. At negative 3 Gs, which means that whatever axis that is, it's moving 3 Gs, so the maximum of 3 Gs in the negative axis direction would be a reading of 0 volts. And then all the way in the positive 3G direction would be a reading of 1.7 volts. After it goes through this conversion, it would go through the ADC to be made into discrete values so that it actually means something when it is sent wirelessly to control.